All right, so let's consider this kind of so-called infinitesimal transformation of the variable q. So this is defined to be just the Poisson bracket of qij x with respect to the vector n. So vector n means that it is diffeomorphism constraint. Okay, so if you do the calculation, it will be your homework. Okay, if you do the calculation, you will find the result. This is just the Lie derivative of n and qij. Yeah, this is just q is a tensor. Just this is the Lie derivative of the tensor q in ij components, and then ij components, and evaluate at point x. And similarly, if you do the transformation for p, ij, so this is again defined by the Poisson bracket with the diffeomorphism constraint. Which is you will just get a Lie derivative with respect to vector n. So sorry, so here it is actually ni ci. So this is vector ni, and c lower I is c upper I lowered index by q. Yeah. So you again get a Lie derivative, but remember this Lie derivative is when you check it, you have to be careful about the Lie derivative because this p is a tensor density. Okay, so you see that the infinitesimal transformation generated. This is called the infinitesimal transformation generated by this function c. Yeah, because it's like the Poisson bracket. It's a little bit you can find this is analog of the time evolution, right? Because this time evolution is just the Poisson bracket between where is the equation motion? Yeah, here it is. You can see that the time evolution is just a Poisson bracket between h and f. So you can view this is an infinitesimal time translation. It's an infinitesimal transformation of this function f, which is the time translation. So here it is again some kind of infinitesimal transformation, but generated not by Hamiltonian, but by this smeared constraint. This is again some kind of infinitesimal transformation, but you see when you do this calculation, you find this infinitesimal transformation is just a Lie derivative, right? And you see this, what is the Lie derivative? And we have learned Lie derivative before, and the Lie derivative is just the infinitesimal version of diffeomorphism. It's just when you have diffeomorphism, you can push forward and pull back tensors, and you make the infinitesimal version of push forward and pull back. It is just the Lie derivative. Then you get the Lie derivative. So what you can see is that the infinitesimal transformation generated by this vector constraint, by the diffeomorphism constraint, it is just the infinitesimal spatial diffeomorphism. So it is just the infinitesimal spatial diffeomorphisms on sigma. Yeah, they are spatial because this n vector is spatial. It is a spatial vector. I only goes from 1 to 3. Okay, so now you can imagine that. Let's work out the other constraint, the infinitesimal transformation generated by other constraint, which is Hamiltonian constraint. Qij Cn. So you have no vector, it means that it is a scalar constraint, Hamiltonian constraint. What you get is, in the end, is this. It's a normal Lie derivative with respect to Q of Q. Yeah. And similarly, again, you see this is again an infinitesimal diffeomorphism, but in the along the time direction, on the normal, let's say normal direction. So remember, this is our spatial slice, and this is our time, and this is the normal direction. Yeah. And then you have shift vector. This is the spatial direction along the sigma. Yeah. So here, the Cn generates the infinitesimal diffeomorphism along the spatial direction, and here the Hamiltonian constraint is actually complementary because it actually generates the normal direction Lie derivative, generate the normal direction diffeomorphism. Yeah, and here it is not exactly NA, but the lapse function times NA, and or this parameter, this test function, and yeah, similarly for P. Okay, but here I have to mention that these equal, it is use some assumptions. So these, when deriving this, you have to use equation motion. So namely the Hamiltonian equations. Hamiltonian equation motion. Yeah. Motion. Okay, so it means, so the meaning of these two equations is that the Hamiltonian actually generate diffeomorphism perpendicular to sigma. This is infinitesimal diffeomorphism perpendicular to sigma. Okay, so here really you get all the diffeomorphisms because you have both diffeomorphism along sigma and also diffeomorphism perpendicular to sigma. Okay, and it is your homework to check them. Your homework is just check them. Firstly, because as you can see, the diffeomorphism constraint is simple. It looks very simple. So this Poisson bracket can be easily computed, and the result is what you get on the right. But Hamiltonian constraint is complicated. You can imagine this Poisson bracket is very complicated if you really compute them. But there's a hint, is that you don't really need to compute them. Okay, so let me give you the hint, is that when you look at the equation of motion, there's a q dot, for example. Let's consider the first one. So there's a q dot, but this q dot, it is just the Lie derivative equals to the Lie derivative of TA with respect to q. Okay. Yeah. Remember why it is true? It's because we are in the coordinate system where this TA is the basis. It's one of the coordinate bases, right? And then remember when we talk about Lie derivative, so when we are in a good coordinate such that the Lie derivative with respect to a vector field, and this vector field is one of the coordinate bases, and then you can, this Lie derivative is just the normal derivative of the components of the tensor. Yeah? So here, what you are computing here, so for example, this quantity is just the Lie derivative of this tensor and taking ij components. It is the same as the partial derivative with respect to time of the ij components. Okay, so which means that you can just relate the equation of motion. The left-hand side is the Lie derivative, right? And then you can just use, and you know this Hamiltonian, it is just a linear combination of the diffeomorphism constraint and Hamiltonian constraint. and you work out the infinitesimal transformation of the diffeomorphism constraint, and then you just subtract, and you know the infinitesimal transformation of the entire Hamiltonian is just a time evolution, right? And then you just use time evolution, subtract the spatial diffeomorphism, and then what you get is the diffeomorphism perpendicular to the spatial slice. So this is the hint. So which means that you don't really need to compute this Poisson bracket for this calculation. You just use the Hamiltonian equation and then subtract the part where you work out for the diffeomorphism, and then you immediately get the right hand side. So which means that the last two equations are very easy to check once you get the first two equations. So this is your homework to work them out. All right. Okay. I think I better stop here. So I'm going a little bit slow, but probably this is a good point to stop. By the way, so here, I think I sent everybody email about the web page of these lectures, and over there you can find some references. And for example, the topic I just discussed, the Hamiltonian formalism, you can find many details. Well, you can find details in many different resources on Wikipedia or some in-video articles. But there you can also find this topic in the book by Ward. The name is General Relativity. I think this is the standard reference of General Relativity class. Yeah, so we use this reference as well. And I think one of the appendix has the Hamiltonian formulation of general relativity. So you can find all the schemes over there, and yeah, maybe some details. Well, so I think this lecture contains even more details than the book, but it's good to have some reference for this. Okay, I think that's it for today. We continue on Friday next time. Yeah. If you have any questions, you have any questions, it's a good time now.
Yeah, I have a question. Hello?
Yeah.
Yeah. My question is related to when you were saying the physical significance of diffeomorphism invariant and the fact that the bulk energy is 0. So I think diffeomorphism invariant tells you that from spatial slice to spatial slice, the energy keeps being is gauge invariant, but it doesn't tell you that the value.
Energy is not gauge invariant. Being energy, it is not. It will. Yeah, energy is definitely dependent on the choice of time, right? Yeah, I mean, for observe some energy, you have used. Yeah, I mean, when we talk about black holes or any other models, and when we talk about energy, we always need to specify the time. Yeah, and the what is, for example, a particle, something gauge invariant. Well, something invariant, something independent of a coordinate is the form momentum. While the Hamiltonian or the energy, it is just the zeros components, the time components of the form momentum, right? And so it definitely depends on the choice of time.
Okay, but I just want to say that okay, so if the Hamiltonian is time translational invariant, then that tells you the energy of the system is 0.
No, definitely not. Well, I mean, all the systems, the Hamiltonian is time translational invariant. For all the systems, the Hamiltonian is a conserved quantity for isolated systems. Yeah. So yeah, all the time the Hamiltonian translational invariant is Hamiltonian is independent of time. So here it is not because of the time translation is a gauge transformation. Well, it is because time translation, it is it's a gauge transformation. So it's not because the Hamiltonian is time translational invariant. It's because the time translation is part of the gauge transformation. Yeah. For all other systems, the time translation is not part of the gauge transformation. Yeah. The time translation is just the time translation. It is it's a symmetry. Yeah. So it's different between symmetry and gauge symmetry, right? So in most of the systems, the time translation is a symmetry. Yeah. But it is not a gauge symmetry. So here is that if your variable and making transform under gauge transformation, yeah, and there you have infinite number of gauge transformations, and your Lagrangian is invariant, and it means that all those coordinate transformations, or more precisely, all those fields transformed under coordinate transformations, they are gauge transformations.
Okay.
Yeah, so that's a special feature here. It's not like the ordinary field theory that indeed you have time translational invariant, but this is the symmetry. You only have finite number of generators for those transformations. And the symmetry group is always finite dimensional, right? You have time translation, spatial translation. The symmetry group is always finite dimensional, but for gauge symmetry, right? And the number one difference between gauge symmetry and ordinary symmetry is that the gauge symmetry is infinite dimensional, while the ordinary symmetry is finite dimensional. Right? So here it is an infinite dimensional symmetry, which is all kinds of diffeomorphisms, and in which your time translation is a gauge symmetry.
So that the value of Hamiltonian has to take the trivial value.
Yeah, it turns out then for all these kind of so-called general covariant system, diffeomorphism invariant system.
Yeah.
This Hamiltonian has to be 0. If you don't have boundary, or the non-zero part of the Hamiltonian, it has to be boundary terms.
Okay. And what? So then Hamiltonian of GR is 0. So then this is sort of, it takes values of the algebra instead of the group instead of the group elements, right?
Say again. It takes value of
the gauge group algebra.
No, the Hamiltonian is just a function. So yeah, the Hamiltonian at least at this moment is just a function on phase space. Just like ordinary Hamiltonian. This is just a function on the phase space, but it's just it becomes 0 on the constrained surface.
Okay. All right. I'll try to.
Yeah. So I mean, when you have the Poisson bracket, it generates the time translation. So the Hamiltonian equation of motion. The Hamiltonian equation of motion tells us that the time translation, the time evolution of the function f, is given by the Poisson bracket with Hamiltonian. So this is Hamilton's equation, right? This is just the meaning of the Hamilton's equation, and you can view this as an infinitesimal, because time derivative is just an infinitesimal time translation.
Right.
Translation is generated by the Hamiltonian.
Yeah, I got it. Thank you.
And this infinitesimal translation is an infinitesimal gauge transformation for GR, for general relativity. So, so Hamiltonian, so the Hamiltonian actually generating the gauge transformation. And so you see all these things are related. So, and the Hamiltonian is a linear combination of constraints, and it generates the time translation, and time translation is a gauge symmetry. Yeah. So I mean, next time I will try to formulate it more in a more schematic manner, so you can better understand what is going on here. Yeah.
Okay.
Is there any other question? Okay. if there's no more questions, so let's stop here.